In this lecture class, we will discuss about protection of SCR. Now, thyristor is a very sensitive device. Not only thyristor, any semiconductor devices are very sensitive. So the devices should be protected from unwanted triggering or because of unwanted signal, the device should not be damaged. Here in case of thyristor, we will discuss DVDT and DIDT protection of thyristor. We will not discuss gate protection of thyristor. Generally, for protecting the thyristor from reverse voltages, a diode is connected across the gate terminal to absorb the voltage spike across the gate terminal. Capacitor is connected. So those things I will not discuss here. Later on, if time permits, we will discuss in detail. So in this class, we will discuss DVDT and DIDT protection of thyristor. First of all, I want to discuss what are the major problems associated with this thyristor. Consider a case when a DC voltage is applied across the thyristor. Then we know that J1 and J3 are forward biased, but J2 is reverse biased. So we can assume that the whole voltage appears across junction J2. Now, for short duration of time, if voltage across this J2 or change in voltage across this J2 is very high or more than forward breakover voltage, then the thyristor will be on. This rate of change of voltage with respect to time may be high to damage the thyristor or unwanted triggering may take place. So it is to be protected from high DVDT. Next is when the thyristor is on or when the junction J2 is breakdown, then all the carriers tries to spread across 4 layers quickly. Because of that, there may be some hot spots created across gate junction, and this hot spot is because of high DIDT or rate of change of current with respect to time is high. Then you can say hot spot created nearby gate junction damage the SCR. In some cases you can see because of this hot spot there may be one kind of a small hole is developed across the SCR. Then you can understand that your thyristor is damaged and go to market to buy a new one. So this DIDT protection is needed. So two kinds of protection basically required, DIDT and DVDT protection. Thyristor is to be protected from false triggering. It may be because of high DIDT or high DVDT. In case the thyristor is turned on by applying a gate pulse, then the carriers tries to spread across the 4 layers as soon as possible. Due to this, there will be high DIDT and hot spots will be created near the gate junction, which can damage the SCR. So to protect it from high DIDT, generally a small inductor is connected in series with the SCR. We know the property of inductor that it will not allow the change in current. So that property is used here to limit the DIDT current. When a DC voltage is applied across the SCR, though gate current is not present, thyristor may be turned on because of DVDT developed across the junction J2. So the thyristor is to be protected from this DVDT. So let's see how we can protect our SCR from these two abnormal conditions. Design of snubber circuit. This circuit is generally used to protect it from high dVdt. And to protect from high dIdt, a small inductor is connected in series with the SCR. So here a circuit is developed. You can see VDC, switch, RC, thyristor, load is there. Now when the switch is made on without any gate current, that means thyristor is off and the switch is closed, then current will flow in the direction VDC, switch, RC, load and back to VDC. Now in this case you can say it is a simple RC circuit. So the capacitor will charge exponentially till VDC, and once the capacitor voltage equal to VDC, then current through the circuit will be zero. That means the capacitor will store some amount of energy across it, and it will discharge whenever favorable condition will be there. Now the favorable condition you can consider that when gate supply is given to the circuit, then once the SCR is on, then capacitor is free to discharge. So the capacitor will discharge through SCR. Here a resistance is connected to limit the discharging current. Otherwise, discharging current of SCR can also create high dIdt and the thyristor may get damaged. So the purpose of resistance is to limit the discharging current of the capacitor. In this circuit, you can see initially the capacitor is charged to VDC. We can assume that for some duration of time capacitor is allowed to charge. That means SCR is off and capacitor is charging through VDC, RC, load and back to VDC. Then once the capacitor is charged, then gate pulse is given to SCR. Then thyristor will be on. Then through SCR there will be two current. First current is VDC SCR load back to VDC, and the second current is discharging current of the capacitor CR SCR back to C till the capacitor is completely discharged. So based on this, we have to protect our SCR from high dVdt and high dIdt. Let's discuss in detail now. In the circuit A, switch is there along with VDC, SCR and load resistance. When gate pulse is given, then SCR will be subjected to two abnormal conditions, high dIdt and high dVdt. When the switch is made on, instantly the voltage VDC will appear across junction J2, and the rate of change of voltage across junction J2 dVdt, if it is more than forward breakover voltage, then the SCR will be on, and once the SCR is on, during the process of turning on of the SCR, the charges will spread across four layers quickly, and because of that high dIdt will be developed across gate junction and the thyristor may get damaged. So thyristor here is not protected from any high dIdt or high dVdt. Let's switch to figure number B. Here an inductor is connected in series with the SCR. So the thyristor is protected from high dIdt because of the basic property of the inductor. Now to protect it from high dVdt, a capacitor is connected along with R across the SCR. So when gate pulse is absent, then capacitor will charge till VDC. So the voltage across SCR is now VDC. Now when gate pulse is applied across the SCR, then the capacitor will discharge through the SCR. So you can say that the problem of high dVdt is solved here because that dVdt is now absorbed by the capacitor. So for dVdt protection, capacitor is connected in parallel with the SCR. This is the property of the capacitor, that Initially, it will provide minimum impedance path and will absorb the power, allowing more current. And then finally, when the voltage across the capacitor is equal to the supply voltage, then current will be zero. So this DVDT spike is absorbed by capacitor. So the capacitor protects the SCR from high DVDT. Now to find the value of this R, C and L, approximate method I will follow, and that is very simple and very effective in designing the snubber circuit. So let's start with this. As we know that at t equal to 0, capacitor has nothing to do. At t equal to 0 means when the switch is made on, capacitor will provide minimum impedance path, or we can assume the capacitor is short circuited. So at t equal to 0 we can remove this capacitor. That's why in the figure C the capacitor is now removed, just to reduce the complexity of the derivation. So now VDC RL RL. So when the switch is made on, current will flow through VDC RL RL if gate current is not there across SCR. Our purpose is to protect our SCR from high DIDT and high DVDT, or maximum DIDT and maximum DVDT. So we will find the value of DIDT maximum and DVDT maximum first. So applying KVL equation in the loop VDC RL RL, we can write equation number 1. VDC is equal to R plus RL into I plus L DIDT. I is the current flowing through the circuit. Solving equation number 1, we can write I is equal to capital I 1 minus e to the power minus t by tau, where capital I is equal to VDC by R plus RL L by, and tau is equal to L by R plus RL. Differentiating 2 with respect to time, DIDT is equal to I into e to the power minus t by tau into t by tau. Substituting the value of tau, we will get a expression DIDT is equal to VDC by L e to the power minus t by tau. So equation number 3 is giving rate of change of current with respect to time. So let's find DIDT maximum. So from equation number 3, it is a exponentially decaying graph. So the maximum value we will get at t equal to 0. So DIDT maximum is equal to VDC by L. Here I am assuming that you know the simple R, RL, RLC circuit with DC excitation. So from equation number 4, if you know the value of DIDT maximum and DC supply voltage, approximate value of L can be find out. Please note that this is approximate value of L. This value will be modified later on. Let's proceed from here. Voltage across the SCR at t equal to 0 is equal to current through the resistance R into R. So I into R. Now differentiating 5 with respect to t. So d VSCR dt is equal to di dt into R. So R is a constant and I is a variable parameter. Our purpose is to protect it from high DVDT or DVDT maximum. So let's find the value of DVDT maximum. So dVSCR dt maximum is equal to DIDT maximum into R, and DIDT maximum value already we have found out, that is equal to VDC by L from equation number 4. So R is equal to L by VDC dVSCR dt maximum. So knowing the value of L, VDC and DVDT maximum, we can protect our SCR from high DVDT. Now this DVDT maximum and DIDT maximum, this value you will find in data sheet of the corresponding SCR you are going to use. And the DC voltage based on your application, you know, then you will find the value of L and R. So equation 4 will give value of L and 6 value of R. These are approximate value of L and R. Now let's proceed to find the value of C. Till now I have assumed that capacitor has nothing to do at t equal to 0. Now as soon as time will increase, then capacitor voltage will also increase. So capacitor will come into play and will oppose the current. So our equations will now change. So let's see that. In this case, for t greater than 0, obviously it will valid for t equal to 0 also. Capacitor is now considered it. So when thyristor is off, current will flow through VDC, RC, L, RL back to VDC. And the KVL equation will be VDC is equal to R plus RLI plus LDI dt plus 1 by C integration of I dt. Now here I am not solving this equation. Directly I am writing the condition, and it will be your assignment number 1 to analyze it from first sem basic electrical, that how you will get the value of this R is equal to 2 root over L by C. Chi will be your damping factor. Its value is between 0.5 to 1. Now once Chi you have selected based on your particular application, and from equation number 4 and 6 you know the value of L and R. So from equation number 8 you can find the value of C, and this value of C will be again approximate value of C, because in equation number 4 and 6 we have not considered capacitor, but here we are considering capacitor. So the effect of capacitor in resistance and inductance is missing. So we have to rectify our values. Now here you can say that once capacitor is there in the system, then after applying a gate pulse across the SCR, then two current will flow through the SCR. First current is VDC SCR L RL back to VDC, and the second current is discharging current of the capacitor CR SCR back to C. So the current through the SCR, it is now more than whatever we have considered in equation number 4 and 6. So discharging current of the capacitor is to be reduced. So whatever value of R we have got, little bit it is to be increased. Generally 30 to 40% more we can choose, so that current through the SCR should not increase more than its rated value or peak repetitive current of the SCR mentioned in the dataset. So a straightforward assumption is that in earlier case, to find the value of R, we have not considered the capacitor voltage discharging current, but here capacitor voltage discharging current we have to consider. Then the current through the SCR will be more than the current whatever we have calculated earlier. So to limit the current within its rated value, R value should be increased. So based on the equation number 6, R will be 30 to 40% more than the value obtained in equation number 6. So once R is increased, so whatever value of capacitor we have got in equation number 8, we can reduce it further for safe operation. That means stored energy across the capacitor, it will be lesser than, and the discharging current will be less to protect it from high DID. And the capacitor purpose is to protect from high DVDT. So both the purpose are fulfilled by choosing the value of R and C this way. So once you have got the value of modified value of R and modified value of C. Then based on the equation number 8, modified value of L you will get. So this will be our final value of L, C and R. So initially we will find the value of R and L without C, and finally we will modify the value of R by 30 to 40% and C by reducing 20 to 30%. Then based on equation number 8 we will find the value of L. So complete design of this circuit can be done this way. So though this is an approximate method, it is quite simple and effective in finding the snubber parameters. So today we have discussed DIDT and DVDT protection of SCR. To protect the SCR from DIDT, inductor is connected in series with the SCR, and to protect from high DVDT, a capacitor is connected in parallel with the SCR. To limit the discharging current, a resistance is connected in series with capacitance. Then approximate method we have selected to find the value of R and L. Then based on the modified value of R and C, we have found out the value of inductor. Like this we can find all snubber parameters across the SCR, and it will work fine in your practical setup. Thank you.